Hello, ladies and gentlemen. Welcome back, everyone. I hope you're doing well today. So, last lecture, we talked about the notion of vectors in a plane. So, in terms of where we're at in the course, we talked about a fair bit of 2.1. And the plan for the rest of today is to work through some of the other details in chapter 2. So we'll do a real brief introduction to the dot product, cross product, and then after the break we'll go into lines and planes. Very good. So vectors are these ways of moving from one point to another point. Hello, welcome, come on in. Greetings. Yeah, so a vector takes us from one point to another. So if we want to move from the origin to a point xy, we can do that by traveling along the vector that we write with angle brackets. Okay? And above vectors, we traditionally put this harpoon to indicate where they're traveling. Okay, so vectors have a couple operations on them. Okay, we can add together two vectors. So if we take the vector xy and we add the vector ab, then we can think of that as sort of adding two journeys together. Right? We travel along xy, then we travel along AB, and that gives us some other way of traveling. Just add together to give us a new vector. That we get by adding up the components of each vector separately. Oftentimes this picture, this sort of geometric picture, is very helpful, I find. Okay. Another operation that we have on vectors is that of scaling. So we can stretch vectors. Okay, so if we have a vector, we can multiply it by some number, and that corresponds to the notion of taking that journey several times. Right? We go from here to xy, and then if we go again, that would be 2 times v. So we can stretch a vector and obtain a new vector. So this operation is called scaling. Yes?
Just like intuition, like when you say u plus v, you draw that whole line. But isn't the endpoint the same as v, so we say y plus v?
Sorry, what was that question?
Yeah, so the endpoint, like the arrow thing, like this one, isn't the same point as v?
Right, so this is the same point as u. So we go along v, and then we go along u, and we wind up at this point here.
Yeah, okay. So, but coordinate from u plus v is x plus a equal y plus v?
Yes. Yeah. Very good. So we go up there. Yes, okay, so we can scale these guys, we can add these guys. Combining these two operations gives us a notion of subtraction. So we can think of a notion of subtraction where we say, well, this will be u plus negative 1 times u. So using the same notation that we had up top, this is following down. Now we multiply in the negative 1. And we can combine them in the usual way. So this is sort of a kind of a typical example of a question you might see in the homework involving vectors to add a couple scalars together. Okay, so take a moment, try and calculate that out. Maybe take 1 minute, put away social media for 1 moment, try and calculate this thing out. Okay, right, so let's see how that works out. So the first issue is that these are sort of in different notations, right? We've got some stuff in coordinates, some stuff with basis vectors. How can we make them the same, into the same notation? Yes?
3 is equal to 2, 3.
Right, so this will be 2, 3. right? So the I goes with the first coordinate, the J goes with the second coordinate. Nice, good. So now we can start working on this expression. We get something like this. We stretch this guy. Stretch this guy. And add appropriately. Can we get a show of hands for 8, 11? All right, great, very good. So it looks like we're mostly at the same spot. Okay. Okay, so we're going to introduce a new operation on vectors that measures, oh, sorry, now it's highlighting cross product, not dot product. And we're going to introduce a new operation on our vectors, which is the notion of a dot product. Yes, sure.
Or this, if we still use the matrix form, is it also fine?
Right, yes, sure, yes. So yes, if you write things as column vectors, as matrices, that's nice too. We'll eventually have occasion to use that as well. Okay, so the dot product is one of these nice things that sort of has surprising consequences. It's like you define it, and then it turns out to have lots of very nice properties. So let's have a look. What this guy does is that if we have two vectors and we dot them together, then we get the following product. We get the entries of the first vector times the entries of the second vector. Okay, who's seen this thing before at some point in their life? Okay, many people. That's great. We've got experience with this thing. Okay, so a nice kind of insight into what this thing does is what happens when we dot a vector against itself. So when we dot a vector against itself, we get something that looks like
The magnitude squared.
the magnitude squared. Yes, thank you. Yes, it looks like the length squared. Nice. So I'm going to write that. This for the magnitude of something. So the magnitude is the same as length. So we'll just define that. Magnitude is a fancy way of saying length. Okay, so now this gives us an insight into what the dot product is measuring somehow. It's measuring something like length. So I want to remark a couple facts about this dot product. Okay, if we have a sum of things, if we have two things added together, then it splits up over the summation. So checking this is a bit of an exercise to check that this holds by giving actual entries to U, V, and W. Another important property of the dot product. Oh, oops, sorry, these should be dots. Ah! Oh no! Oh, this is terrible. Just to say a little bit about that typo, because it's an interesting typo. In some books, you'll see